Have you ever seen something that looks like this? Maybe in a textbook, or on the internet, or someplace else. This is called a chemical equation, and it's a representation of a chemical reaction. This particular chemical equation represents a chemical reaction between magnesium and oxygen to form magnesium oxide. It's this reaction here. Chemists use chemical equations to help them better understand chemical reactions and to make predictions. Chemical equations are made up of chemical formulas for the elements and compounds involved in the reaction. Just to review, every compound has its own chemical formula that consists of chemical symbols for the elements in the compound, subscripts indicating the number of a particular atom in that compound, and remember the subscript always refers to the atom to the left of it. Here's an example. In the molecule H2O, there are 2 hydrogen atoms and 1 oxygen atom. Sometimes there are parentheses containing pairs or groups of atoms that are bound together and exist as a unit. The subscript outside the parentheses tells us how many groups of these atoms there are in the compound. For example, here we have magnesium hydroxide. We have 1 magnesium atom, but we see that we have 2 hydroxyl groups. Those are the OH groups inside the parentheses. So this is going to give us 2 oxygen atoms and 2 hydrogen atoms. So we have 5 atoms total in this particular compound. Chemical equations combine chemical formulas together to show how the reactants are used up and how products are formed. A plus sign on the reactant side indicates that there are 2 or more reactants being combined. A plus on the product side would tell us that there is more than 1 product being made. And here's an example of a chemical reaction in which there's more than 1 product being made. The arrow between the products and the reactants tells us if the reaction is going in one direction or if it can go in both directions. We use a double arrow like this one to indicate that a reaction can go both ways. The coefficient is a number that is sometimes found on the left of the compound or element. It tells us the number of copies we have of the compound or element. In this example, the coefficient 2 in front of the magnesium atom tells us that there are 2 magnesium atoms in each reaction. There is no coefficient in front of the oxygen molecule, and this means there's only 1 of these in the reaction. The coefficient 2 in front of magnesium oxide tells us that 2 copies of this compound are produced during the chemical reaction. Sometimes it's helpful to use a particle diagram to make sense of what's going on in a chemical equation. We've taken our magnesium oxide reaction equation here and see we can draw out 2 magnesium atoms plus 1 molecule of oxygen, and this is giving us 2 copies of magnesium oxide. As we said earlier, chemical equations are a way to represent or model chemical reactions. Now let's see how this works. In this reaction, chlorine gas is reacting with copper metal to form copper 2 chloride. And this is the chemical equation for that reaction. In this reaction, solid aluminum is reacting with liquid bromine to form aluminum bromide. This reaction has this chemical equation. In this reaction, potassium iodide is reacting with lead 2 nitrate to form lead 2 iodide and potassium nitrate. We have 2 products in this reaction, and this is why we have a plus on the product side as well as on the reactant side. The take-home point here is that these chemical equations represent real phenomena. They represent real chemical reactions. In any chemical reaction, mass is neither created nor destroyed, and this is called the law of conservation of mass. Sometimes you'll hear it called the law of conservation of matter. You should always have the same number and type of atoms on the product side as you do on the reactant side. If you do, it means your equation is written correctly, and we say that the equation is balanced. But if you do not have the same number of each type of atom on both sides, it means that your equation is not balanced and that it does not represent what is really going on in this reaction. When you have an unbalanced equation, this typically means that one of your coefficients is missing from your equation, or it is incorrect. And we can fix this by balancing the equation, and this is something you will learn to do in the future. But even if you don't know how to balance an equation, it's not too difficult to figure out if an equation is balanced, as long as you know how to count the atoms. So let's give this a try, and we're going to take our magnesium oxide reaction equation here. Now what we're going to do is we're going to look at the number of atoms on the reactant side and on the product side separately. So let's start with the reactant side. We see that we have 2 magnesium atoms, and then we have 1 oxygen molecule, and that subscript tells us that there are 2 oxygen atoms in that. So we can add these up and we get a total of 4 atoms. Now let's look at the product side. The coefficient 2 tells us that we have 2 copies of magnesium oxide. That means we have 2 magnesium atoms and 2 oxygen atoms. Now, if we compare the number of magnesium atoms on both sides of the equation, we have 2 on each side. Let's also compare the number of oxygen atoms on both sides of the equation. We also have 2. We have 4 atoms on each side. This equation is therefore balanced. We can also say that mass has been conserved. Here's another example. We have methane reacting with oxygen to form carbon dioxide and water. Sometimes it's easier to count atoms if you draw a table like this one. Well, let's go through this, and we're going to look at the reactant side first. We have 1 carbon. The subscript to the right of the hydrogen tells us that we have 4 hydrogen atoms, and we have 2 oxygen molecules, and each of those molecules has 2 oxygens in it. This means we have 4 oxygen atoms total. If we add these up, we get a total of 9 atoms on the reactant side. Now let's move to the product side. We have 1 carbon atom, and we have 2 copies of water. Each water molecule contains 2 hydrogen atoms, so we have a total of 4 hydrogen atoms. Now we have oxygen in both of our product molecules. We get 2 oxygens from the carbon dioxide, and we get another 2 oxygens from the 2 water molecules. This gives us 9 atoms total on the product side. Notice that our equation is balanced because mass has been conserved. Sometimes with the coefficients and the subscripts, it's hard to keep things straight. So another trick we can use to solve this problem is to draw out our reactants and products using particle diagrams. And we can do so here. We can draw out the methane and then our 2 oxygen molecules, each of which has 2 oxygen atoms in it. We'll draw out our carbon dioxide and our 2 water molecules. And then all we would have to do is count the atoms. And we find that mass is conserved and our equation is balanced. In this reaction, we have phosphorus pentachloride reacting with water to form phosphoric acid and hydrochloric acid. Let's take a look at the reactant side. We have 1 phosphorus, 5 chlorine, 8 hydrogens, and 4 oxygens, and that gives us a total of 18 atoms. On the product side, we have 1 phosphorus, 3 chlorines, 6 hydrogens, 4 oxygens, and that gives us a total of 14 atoms on the product side. The reactant side has 2 more chlorines and 2 more hydrogens than the product side does. This equation is not balanced because mass is not conserved. We can also look at this equation using a particle diagram like this one. It's pretty easy to see here that we have more chlorine atoms on the reactant side than we do on the product side. And if you look closely, we can also see that we have 2 more hydrogens on the reactant side than we do on the product side. In summary, chemical equations represent chemical reactions. They are made up of chemical formulas for the elements and compounds that are involved in the reaction. Coefficients tell you how many copies of each molecule or compound are in the reaction. The law of conservation of mass says that mass is not created or destroyed during a chemical reaction. In a chemical equation, the number and types of atoms in the reactants must be equal to the number and types of atoms in the products if mass is to be conserved.